Hello, welcome to your lesson on probability. We will look at dependent and independent events in this lesson. Let's get started. Let's go back to just some symbols to recap symbols we should know. This symbol here means intersection. It often means A and B. So if two events occur at the same time or one after another, we use this symbol. This one here means union. It is known as A or B. It means events A or B or both occur. Here we have the complement, which means not A, so everything except for event A. And here we have conditional probability. And this is what this lesson is going to focus on. These ones we looked at recently. Today, let's focus on this. This means A given B, or event A occurs given that event B has occurred. In terms of Venn diagrams we've already seen, this means that we're looking at, when we say given that B has occurred, we're looking only at the B circle. So instead of looking at all the things in the whole rectangle, all the possibilities, we're saying, let's look at only B, and now we want to see what's the chance of A occurring within that B circle. So A occurring within that B circle is this portion here. That is the A portion within the B circle. Okay, so now let's move on to independent and dependent events. So two events A and B are independent if the occurrence of each event does not affect in any way the occurrence of the other. So again, one thing occurs, it does not change the probabilities of the second thing occurring. Those are independent events. So it says equivalently, knowing that A has occurred does not affect the probability that B does, and knowing that B occurs does not affect the probability that A does. Now, two events A and B are dependent if they are not independent. Well, that's a funny definition, but basically what that means is that now, if one event occurs, then, or what happens in one event, like whether it happens or doesn't happen or something like that, it affects what happens with the other one. So the probabilities of the second one change based on what happened in the first one. So here's an example. We have a bag. It contains 2 red, 1 green, and 3 blue stones. You reach into the bag and take 1 stone. Then you reach in again and take another stone. In this first scenario, scenario A, after drawing that first stone, you return it to the bag. So you reach in, pull something out, look at it, and then put it back in, and then draw something again. So are these independent or dependent events? Hopefully you answered independent, because since you have drawn a stone but then put it right back again, now your probability in that second draw has not changed at all because you're resetting the bag by putting the first stone back in. So the probabilities remain exactly as they were in the beginning. That's independent. So now we're going to use the independent formula, and we're going to find out what is the probability of having a blue stone, looking at it, putting it back in the bag, and then drawing a red stone. Okay, as you may remember, for when we have one event followed by another, we just multiply the two probabilities. So here's probability of getting a blue stone times probability of getting a red stone. And the probability of getting a blue stone is 3 out of 6 because there are 3 blue stones out of the total 6 stones. And then, since you return that return that stone to the bag, your probability remains the same. And the number of stones in the bag remains the same. So we still have 6. So now drawing a chance of getting a red is 2 out of 6. That becomes 6 over 36, which reduces to 1/6. Okay, same bag of stones, but the scenario now says after drawing the first stone, you do not return it to the bag. Are these independent or dependent now? Well, hopefully this time you changed your answer to dependent, because if you do not return the stone, so you take a stone out of the bag, you keep it. Now when you reach into the bag again, all the probabilities change because the number of stones in there has changed. So that's dependent. Let's use the formula for dependent events. So what's the probability of getting a red and then a green? Well, here we go. This time we're using the dependence formula. So we have probability of red and then probability of green given that red has occurred. Maybe you didn't know how to use this symbol yet, but let's look at red. Okay, the probability of red is 2 out of 6 stones. Great. Now, the probability of green is still 1 stone left in there that's green, but since 1 red is gone, now there's only 5 stones remaining, so it's 1 out of 5. So that's where the dependence comes in. Notice that went down. This changed. This probability changed because this thing happened. So we're saying the green probability, which in the beginning would have been 1 out of 6, is now 1 out of 5. So green has changed because of R. So green, given that R has occurred. All right, so that's what that symbol means. And that reduces to 2 out of 30 and 1 out of 15. All right, so let's recap those kind of formulas we should know now. So first one is the formula for dependent events. Do you remember what this is? Well, we have probability of B there. When you're looking for probability of A given that B has occurred, we find the intersection and we divide by the B. And that's, if you think back to the original Venn diagram, which I think is worth going back to right now, right here. When we're finding the probability of A given that B has occurred, again, this is the portion, we're looking at the B circle, and we want to know the portion A is what portion of the B circle. So here's the A portion, which is the intersection of those two, divided by out of the B circle. So that part, the A part of B, out of the whole B. All right, let's go back to here. That's kind of a key idea. So that's the formula that's showing us what that Venn diagram showed us. We have the intersection, which is that little part in the middle, divided by the B circle. So A given that B has occurred, which means we're looking only at things within B. All right, next formula. Based on this one, we can say therefore probability of A intersection B. So take this formula here, rearrange it solving for this. And you get this, right? Because this part using algebra just multiplies over to this side. So we have probability of intersection is probability of B times the probability of A given that B has occurred. And again, that's just what we looked at in the bag of stones question. We're just multiplying the two probabilities, but this probability has changed when there's dependence. All right, next formula. Probability of A such that B, or given that B has occurred, equals probability of A. When does the A, in other words, the A probability not change? Because here's probability of A, and it's equal to this one. So if they're equal, it means this one has not changed because of event B. So when does that occur? Well, only if A and B are independent. Because if they are independent, then the probability of A does not change, even though B has occurred. So these are the same. All right, how about this one? Therefore, probability of A intersection B equals what? Well, it's just those two multiplied. The intersection is those two multiplied if we have independent events. Again, only if we have independent events. Whereas this one you can use always. This one only occurs when we have independent events. All right, let's use these formulas. So here's your first problem. We have this Venn diagram. Please read this. Please answer A to start. Well, let's take a look at how you did. Here's A. So it says find the probability of S and S given that M has occurred. So probability of S is this whole circle, 8 out of the total, which is 20. 8 out of 20, which reduces to 2 over 5. And then probability of S given that M has occurred. So now we're looking at the S portion within the M circle only. So here's the M circle given that M has occurred, see? And then the S portion is this. So 2 out of 5. Notice those are the same. So what does that tell you? If these two, if the probability of S is the same as probability of S when M has occurred, if those are the same, the events must be independent because the probability of S has not been adjusted after M occurred. So they must be independent. All right, try B. Let's take a look. In B, there's another way to show these are independent, and that way is to multiply these two probabilities. So it says find that, and that multiplied is 2 out of 20. And that is actually the same as the intersection when you look at it from this diagram, because here's your 2 out of 20. Since those are the same, since that times that is the same as that, we know they're independent because, again, the intersection, this times this would only be the intersection if they're independent, because otherwise you'd have to have m given that s has occurred to get the intersection. All right, next question. Please take a look at this one and see if you can answer part A to start. Okay, A is pretty easy. You can say without any calculations that these two events are independent, because whether your name is David or not David has no impact of whether you as a person like coffee. So the name of a person does not determine coffee tastes, and likewise whether somebody likes coffee or not does not have any effect or determine their name. All right, so now try B. Solve both of these and let's see what you get. All right, in B we have the answer for the first one, C intersection D. You just multiply those two. In A, we already determined that these are independent. So since they're independent, you just multiply one probability by the other. You don't have to worry about adjusting the second probability based on the first. So just multiply them, you get that. In the second part, the union, if you remember the union formula, is probability of one of them plus the other minus the intersection. Okay, and that works only for events that are not mutually exclusive, right? So we subtract the intersection from those two added and we get that. There's the formula there. Okay, so let's move on to C. Give C a try. Okay, in C, we know they are not mutually exclusive. If you remember, mutually exclusive in a Venn diagram would mean two circles with no overlap. They're two circles that are separate of each other. They exclude one another. So now, and if you remember talking about that, it meant that there's no intersection between those two circles. So that's what we found out in this question. We solved C intersection D and we found it to have a value. Therefore, it's not equal to 0. If we did find this to be 0, we could say they're mutually exclusive because that would mean there's no overlapping circles. All right, and this is our last question now. So still practicing all these formulas for probability. Please read it and try A and B. Okay, let's take a look. So for A, probability of S is 7 out of the total, and that's what's showing here, the number of things that are in S divided by the number of things in the universal set, which means all the things here. So that reduces to 1 over 4. And probability of I is 8 out of the total 28, which reduces to 2/7. Okay, try C and D now. Okay, so C, these are two dependent statements here, or conditional probability. So S, given that I has occurred, so the S portion out of the I circle, right? So the S portion, here's the I circle, 8 things, and the S portion is 2. So 2 out of 8, which reduces to 1/4. Same thing now for I, given that S has occurred. It's the I portion of the S circle. So here's the S circle, the I portion is 2, so 2 out of 7. Here we go. Okay, try E and F. For E, we're looking for the intersection. Well, we can clearly see it here. 2 out of 28, which reduces to this. And F, we're looking for the multiplication here of the two. So 7 28ths times 8 28ths, or we had the reduced fractions here, which is 1 over 14. And the final question here is determine whether S and I are independent. Well, we would know they're independent if the intersection is equal to S times I, and they are. So we have the intersection is equal to these two multiplied. That's independent. We would also know they're independent if if one of them like these dependent statements here are the same as these. So we can compare PS, given that I has occurred, to PS, and those are the same. If I go back, here's PS 1/4, and it's the same as